Hello everyone and welcome back to Clinical Cousins YouTube channel, where today we're going to go over the cardiac cell electrophysiology, specifically the ventricular cell. Now this is very important to know because it will provide us with certain clues as to why our patient is experiencing EKG abnormalities. For example, if we are seeing peaked and sharp T waves, such as this, our patient may be experiencing hyperkalemia or too much blood potassium. And if our patient has a prolonged QT interval, meaning a QT interval that is too long, they may have low calcium or low magnesium, known as hypocalcemia or hypomagnesemia. Now, we must know how the cardiac muscle contracts. Basically, there are proteins called actin and myosin that begin to overlap when they are stimulated to contract by the electrical system of the heart. The left ventricle has many layers of these filaments and is thick because it must pump blood to the entire body. And the right ventricle is less thick than the left ventricle because it must pump only to the lungs and back to the heart. Inside of each of our cardiac myocytes, or muscle cells, there is more potassium and magnesium. And outside of the cell, there is more sodium, calcium, chloride, and bicarb. Now, the actions of the sodium potassium ATPase along with potassium and chloride leaky channels helps give our cardiac myocytes a resting membrane potential of around -70 to -90 millivolts. If you only remember one, remember -70 millivolts. Now, if you didn't understand how I just got there, or you feel like you don't have a very firm grasp of the cellular basics, you should watch our short cellular physiology series. Here's what happens when a single cardiac myocyte becomes excited. For your convenience, I have drawn a cardiac myocyte with all the channels of different electrolytes that we will use, and I will draw this graphically to represent the millivoltage change in the cell. Now, what we must know is that excitation is broken up into different phases. It involves the influx and efflux of certain electrolytes. First, I've drawn the baseline, which represents threshold potential. Now, in our cardiac myocytes, specifically in our pacemaker cells, we have sodium funny channels that allow a trickle of positive sodium inside our cardiac myocyte. This slow trickle of sodium is called phase 4. This continues until the cell reaches threshold. And at this point, voltage-gated sodium channels open and a flood of sodium comes into the cell. This is called phase 0 or upstroke. Notice we've gotten a lot more positive. Phase 0 is the exact moment when depolarization occurs. Now, this depolarization cannot last forever. And at the very top is when our cell is the most positive, and this positivity opens our voltage-gated potassium and chloride channels. This allows our cell to rid itself of positive potassium and allows negative chloride into the cell. The result is called phase 1 or initial repolarization. This phase 1 makes our cell more negative. However, something interesting happens. Our slow voltage-gated sodium and calcium channels open and allow positive sodium in and positive calcium in to our cardiac myocyte. This is called phase 2 or the calcium plateau. Remember that calcium is needed for muscle contraction? This calcium that is introduced to our cardiac myocyte during phase 2 is what stimulates our muscle contraction. Calcium binds to the troponin complex, which result in the myosin-actin cross-bridge formation. Basically, the potassium and chloride negative effects are battling the sodium and calcium positive effects during phase 2. These want it to become more negative, these want it to become more positive. Lastly, we have our slow voltage-gated potassium channels that open and allow positive potassium out of the cell. This is what causes our cell to return to its original hyperpolarized state. This is called phase 3 hyperpolarization. Now, we must note that the rate or speed of phase 4 depolarization is different for pacemaker cells. The SA node has the fastest phase 4 depolarization, and the Purkinje cells have the slowest rate of phase 4 depolarization. Conveniently, the rate of phase 4 depolarization gets slower as we go from the SA to the AV to the bundle of His, and so on and so forth. Therefore, the SA node will fire and control the pace or heart rate for the entire heart. This is because the SA node has the fastest rate of depolarization, or the fastest sodium funny channel influx. As always, thank you for taking the time to learn with us today, and remember to like and subscribe for more content.